Okay. So it's a second and hopefully the third one. So, okay, surprisingly for me, my original plan is still on the blackboard. But let me just, before we start the second part of this plan, let me just recall the setup we discussed last time. Mostly the setup was, I was trying to establish a kind of dictionary commonly used in the theory of integrable systems. So the first point I was trying to make is that despite a variety of forms in which this integrable system come to life, they all share some common features, namely integrable system in a way, system is a compatibility condition, of overdetermined system of linear problems. So it's, this is the first point I want to make. In that sense, if we think about integrable system as a dynamical system on certain phase space, I'm not using the term phase space as right now as in the Hamiltonian theory, just a space on which our dynamical system evolves. So I will always think about this phase space is a space of operators depending on a spectral parameter. This is the starting point. So this is the phase space, the space on which our dynamical system lives. At the moment, I'm not going, or last time, I was not touching the evolution. I was just fixing my attention first on a space of operators without any connection to any forthcoming integrable systems. And there were two basic examples I present. The first one is a space where L is just simplest operator. It's just a matrix. Matrix depending in a rational way on some spectral parameters. So L is U naught plus some Ui Z minus Zi. This is our space of operators again. You can think about entries of U naught and Ui as coordinates on this space, but for me, this space is L. Okay, because usually there is some conjugation involved, so I can choose a gauge in which U naught, for example, it's convenient. U naught I delta ij. So by conjugation, I can always make one of the matrices to be diagonal. And for simplicity, for example, I can assume that it's a regular, so these diagonal elements are different. Another example I discussed last time, where L is Just the usual Schrödinger operator. Now, the phase space is the space of functions of one variable, but again, I think about them as an operator. And again, the difference between finite dimensional and evolution integrable system is that the latter can be considered as integrable system only when you specify some class of functions. If you say u of x is any function, there is no a trace of integrability in KdV equation. There are no integrals for KdV if u is not periodic. Nothing. Okay. So the first point, there is a space of operators. One or other form, there is variety, but all of them are space of operators. Slight modification, if you think about L to be not just a meromorphic function on some algebraic curve, you need just refinement. This is the case of Hitchin system. You should twist. I can more explicitly write. There is no difference between the first example and Hitchin system at all. Okay, so this is the starting point. On a space of operators, by the way, last time I explained why, although there is no spectral parameter at all here, in a hidden way, if you say that u of x is periodic, plus 1, for example, then you can just restrict. You should think about this single operator as a family of operators depending on z, because you can restrict this operator on a space of function whose monodromy is just exactly z. In that sense, this is the family of operators depending on z. So, the next point I explained last time was spectral transform. For given L, we assign, in general data, spectral curve and a divisor. So spectral curve is eigenvalue of an operator. Divisor is an eigenvector. And in the first example, in example 1, the definition of gamma was very simple. You just consider the characteristic equation k minus L of z, and that is some polynomial in k, polynomial rational function in z, and this is just the curve. Eigenvalues of L depending on z, and this is the algebraic curve. For other cases, definition similar. It's not essential. So, we computed last time. Okay, in dimension of L of dimension of this space of L of z in example 1, it's very easy to count. It's R coming from these diagonal elements plus n number of poles, punctures to n times R squared. This is the dimension of our phase space. Number of parameters in R, in the coefficients here, we computed, it was n times r plus 1 over 2 plus r. So it's, roughly speaking, half of this dimension. And this is the indication that actually it looks like a integrable systems. So genus of gamma in this case, so this is algebraic curve, it has a genus, you can compute using Riemann-Roch theorem, and the genus is n plus again it's r minus 1 over 2 minus r plus 1. So the genus. And degree of divisor, so number of points involved in D is G plus R minus 1. Later, probably, I'll explain how one can compute. It's very simple. So overall, it becomes R minus 1 over 2. And combining, you see that it is the sum of these two dimensions is exactly the dimension of our phase space. Of course, it's not a proof that generically it's one-to-one correspondence, but I will try to avoid the proof because I would like to avoid a use of Riemann-Roch theorem. A couple of a little. Who knows what this Riemann-Roch theorem is? 1, 2.
I mean, n is missing, I guess.
Sure. So the proof state, in fact, L, gamma, and D. So this is the correspondence that is assigned to L, spectral curve, and the divisor. It's called direct spectral transform. The statement is 1 to 1 on an open set. It's very simple and it's trivial, but let me just skip this part. Maybe counting the dimensions would be sufficient. But, okay, probably if time permits, I'll do this exercise later. Okay, so what we just did, we took a space of operators and assigned a certain data on it. And that has nothing to do with any dynamical system. It's just saying that the space of operators is, okay, Lagrangian, which is not, again, until now it's forbidden word because I didn't introduce anything from Hamiltonian mechanics. But actually it's going to be a Lagrangian fibration on a space of spectral curves, and the fibers are Jacobians of this curve. So this spectral transform gives you a picture of your space of operators as a fibration. We'll talk more about it later. Now, what about dynamical systems? Now I want to define on the space of operators in a universal way some vector fields, some dynamical systems. And again, I'll do it using just first example, but I want to stress that it's very general and has nothing to do with the choice of an example. So vector fields it's a Lax equation. I want to define on a space of operators a certain dynamical system, and I write it by definition. This is the definition of certain vector field on a space of L's. Of course, it's not a definition at all, because what is A here? I know the letter L. L is a point of my phase space. So you can make sense of it only if you say how A depends on L. If you can define A as a function of L and put it here, then it's going to be some evolution equation on the space of L. Usually when people write AL Lax equation, they don't stress that it has sense only if you know how to express A in terms of L. And the point we are going to discuss next would be the following. The Lax equation defines A as a function of L. Almost, and we see the meaning of this almost uniquely. So the choice of this representation actually defines the flow by itself with a very little ambiguity, namely, okay, this is our L. I want to define some evolution of my matrix depending on Z in a way L of Z equals commutator A of Z L of Z. And that has to be satisfied identically in Z. So what is A? Again, as I said, it's almost uniquely up to some very little ambiguity left. Okay, if L is a rational function, it is natural to expect that A is a rational function of Z. For example, let's choose the simplest way. V divided Z minus mu. Because you can split, factorize any rational function. Let's choose the simplest one. And C. So A is at this moment, it's arbitrary rational function. Mu, again, let's for simplicity choose mu not equal to Zi, just somewhere pole. When this equation is well defined, the left-hand side is a function with poles at point Zi, right? The right-hand side is a rational function with poles at Zi's, where L has poles, and mu also. So in order to be satisfied this equation, it requires that there is no pole at least no pole at Z equals mu. The right-hand side. The left-hand side has no pole. The right-hand side should be also free of pole at so it tells you that V commutator with L at mu is 0. So there is no pole. That means that the residue commutes with L at this point. Okay, can we solve this equation? Very easily. You just say V is L of mu to some power k, whatever. This is, if you're looking for gauge invariant solution, this is the only solution. So we define, so from this equation, first we define A. And in this way, A becomes a function of L. Now we can plug in and get a well-defined system of equations. In a similar way, I can consider, probably I'll do it later.
K is an integer, but it's a fraction.
No, integer. Whatever you want.
Anyway.
No, it's integer, because otherwise there's some ambiguity. You should choose something. But if you want that to be just a function of L without any ambiguity, k is an integer, arbitrary integer. Okay. Negative. Probably, but okay, let's for time being the matrix can be degenerate, so negative integer is not working always. So to be on safe side, it is positive. Even with this positive, so we have not just one Lax equation, we have, let's be called T mu k, because of L equals commutator A of L. And in this definition, we made a choice, mu and k. So for any choice of number of mu and k, we define a vector field. Right? Because this is our A, which depends on the choice of mu and k. So we have not just one, we have a family of flows.
So in particular, you can choose mu so that L of mu is non-degenerate, and then you have more.
Okay. In this case, you see, I need only, because the phase space is finite dimension. It's clearly all of these flows with starting, they will be linear dependent. So I don't need too many of them. I want to make a point. Again, on a space of operators, there is always a choice of certain flows. What is the essential point is all these flows commute. So actually we have not just one flow, we have always a family of commuting flows. So there is some ambiguity in the choice, in the definition A as a function of L. What that you do, you have a commuting family of flows. Okay, this is one line exercise. Let me just show you. Okay, so what does it mean that two vector fields defined by this equation commute? That means that this is dt, let's call k mu minus L to the power k mu z minus mu. This is d over dt k mu minus a of L with indices k and mu. This is what stands here. We should check that these two operators, L lambda minus k L to the power k L lambda, this is our V, the residue of A, Z minus lambda. You need to check that if this is our A, if L evolves according to Lag's equation, then these two operators commute. Okay? So what does it mean that these two operators commute? Let's check that the left-hand side has no residue at z minus mu. So we have the dl lambda, L to the power k, L to the power k at mu. This is the commutator of these two terms. That plus mu minus lambda, L to the power k of mu, L to the power L at lambda equals 0 commutator. But that is exactly the equation we have here for this field. Okay, so again, the first point I'm making, there are certain family of laws. They are commuting. Checking of commutativity of this flow is one-line exercise and much simpler than verification that certain Hamiltonians are in involution. In all this theory, everything can be done just in a way opposite to classical point of view. How usual in classical mechanics, Hamiltonian mechanics, integrable systems are described. You have a family of functions in involution, then the corresponding flows commute. In the theory of integrable system, it's much easier to construct flows and to check that they commute. It is really one-line exercise. We did it in this example. In all others, it's not much harder. The third lecture would be, I will explain why they are all Hamiltonian. It's a different story. Because for solving the equation, you don't, sorry? There was a question?
Yeah, but there should be additional terms because less than term.
No, I'm just looking on the residue at z equals mu. At z equals mu, this is the residue that comes from commutator this at that term. But this is the same, you check for there is no, you should, for this equality, you check that there is no residue at mu and there is no residue at lambda. I wrote the equation that there is no residue at mu. The same is for the second. Of course, there is the second equation, but it's on the same footing. There is no reason. Okay. Okay, so on a space of operators, we define the flows. The next point I want to make is that the spectral transform we introduced before actually solves these equations. Okay. So the next point will try to explain that flows defined by Lax equations are linearized by the spectral transform. Okay, so we have L. Starting from L of Z, we define spectral curve and divisor. And as I said, it's one-to-one correspondence. Now, we have L depending on T according to this flow, or according to the whole collection T, K, mu, or whatever. Because since all the flows commute, that can be easily established. You can consider the flow, the action of the whole group of times on L. So L is a function of Z, T, and dependence of T in T is defined by this equation. Okay, so for each T, we define the corresponding spectral data. Last time, just it's easy access. Okay, it's easy to see that the Lax equation by its form preserves eigenvalues. Since it preserves eigenvalues, the spectral curve is an integral. So it's a generating form of all integrals of this equation. D becomes a function, this divisor, this set of points that are poles of our function, depend on T. So we have some nonlinear dynamics on the space of L. We have trivial part on one half of spectral data. We have some, who knows how, some complicated deformation. I want to explain why this part is also linear. It's again, and I'll try to do it in a more or less complete generality. Okay. So my next goal to explain how to solve the part of this story, because at the moment when I can solve the equation, the evolution of flow of this line bundle in T, I am done, because it's a linear dynamics, then I solve and we'll have solution of the Cauchy problem for initial data. Okay, so let psi of T, P be an eigenvector of LT of Z. So P is a point of the spectral curve. So for each point of the spectral curve, we have a eigen vector of a matrix L by definition of the spectral curve. So what is the equation of psi? So if L evolves according to Lag's equation, psi evolves also somehow. Okay, let's compute. What is it? Since, again, here T is any of our times, it's just, and A is any choice of the floors. Since the operator dt minus A commutes with L, and this is our equation, means that applying this operator to psi, I will get again a eigenvector. So the equation is psi times f. This is just trivial corollary of the fact that this operator commutes with L. F is, so this is eigenvector with one or other normalization we choose. And this is just its proportional. So it's again eigenvector. Any two eigenvectors differs by multiplication by a number. So we have the equality that f is a scalar function on gamma, on the curve. So psi is a TP, it's a vector, and I write it from the right just to indicate that this is scalar function. Okay, let's see what are f at Tp has poles of order 2 at gamma s, at poles of the function, at poles of eigenvector psi. Why? So we have that psi of Tp, for each t it has a pole at certain points of our devices. So it has z minus gamma s of t, or okay, phi s of t plus O of 1. So I'm just using Lorentz expansion of my function in the neighborhood of pole. Okay, so when of order 1 at the point. Why? Okay, I take the derivative. Phi has a pole of order 2. So in order to have the equality, it's clear that f has to be a function with policies. Moreover, I can say that this function f of t, locally its expansion is z minus gamma s of t plus regular term. And what is the residue? It is gamma s dot. I just take the derivative of phi, and using this equality, I compute how looks the singular part of f from this equation. Okay, that seems very trivial, very elementary, but it's a basic. And this computation leads us to the following very important problem, corollary, namely, consider the function, the vector function, psi tilde of Tp, which is just psi of Tp e to the power negative integral from 0 to t f of Tp dt prime. I'm just making a gauge transformation of my vector. By this choice, the result is that this psi tilde is first of all, it's an eigenvector of the L operator because we just multiplied by some function. If you plug in this expression into that equation, you see that it now solves the other equation, namely this psi tilde is a solution of the equation dt minus a is 0. I just, by making this gauge transformation, I just remove the right-hand side of this equality. It's trivial transformation. Okay, now, what are analytic properties of psi tilde? Psi tilde has poles only at d at 0. So there are no poles of this function away of the divisor corresponding to initial data. Let us see why it's so. If you just, so this is f of t, you can easily integrate this expression. It becomes log z minus gamma. After being put here, it becomes z minus gamma of t, which cancel the pole of psi. So this factor has 0 where psi of t has poles. So there are no poles. We just freeze all the dynamics on the space of the divisors. Nothing is left. D is now not evolving in T in the same way as gamma doesn't evolve. Okay, so where is the remains of this non-trivial dynamics? And the remains is the following. f of Tp has poles of order L. Has poles of the point at the points of the divisor d of t, and poles at points on gamma over z equals mu. Okay, let's see. Again, we are looking on this equation that has to be satisfied. A has a pole of at z equals mu. So, in order this pole to be cancelled, F must have a pole. Let's see, what is this pole? Okay, this is z equals mu. This is a point. There are pre-images on our spectral curve over z equals mu. And we have the equality A psi equals psi f mod regular part. Because everything is holomorphic at this point except A and F. So what is that equality tells you? That psi is an eigenfunction, eigenvector of L. Oh, it's not surprisingly because we know that A is at this point the residue. Oh, probably it's V, the residue. Not A by itself, it's a residue. And if it's the residue of F. But this residue is L to the power K. So this psi is the same eigenvector as for L. That's true. What is F here? It's eigenvalue of this operator. Right? So it is Kj. This is the so F is some eigenvalue of this matrix at this vector to some power K. Okay, so this is just telling you because the singular part of F is, okay, what is it? How it evolves with time. Doesn't evolve at all because it's an integral. Eigenvalue of L are integrals. So, what is the behavior of psi tilde at any of these points? Psi tilde is something regular times e to the power nu j k t, because just I'm taking the integral of a constant. So the singular part divided by z minus mu. So the function psi tilde has exponential singularity. But the crucial thing that the dependence of time is linear. Again, In order to define Lux equation, we saw that the matrix A has to be, its singular part should be some constant function of L. L is independent, characteristic polynomial is independent of T. After this gauge transformation, which can be thought as a time-dependent normalization, what happened? We just construct an eigenvector for two linear problems whose poles on the curve are independent on T. And the only dependence on T is hidden in the exponential singularity. And this exponential singularity is linear in T. And that's all. This is the linearization. At the end of the day, we can write the formulas, just see explicitly why it's linear on the Jacobian. But the relevant fact is the following, that given L of T, we have gamma of and D of 0, so we're solving the Cauchy problem. So solving evolution of T according to Lux equation is defined by certain fixed data, curve and a divisor, and linear exponential singularity. And that's all you need to know to explain why the integrable system is integrable. It is linearized by this simple gauge transformation. I think it's time for me to make a break and then we'll continue. By definition, there are standard notions, meromorphic functions, it's meromorphic function on the curve. General notion of Baker-Hazer function, it's meromorphic function except exponential singularities at any point. So what we just prove, this is that the common eigenvector for two linear problems is a Baker-Hazer function, yes. I was trying to avoid use of terminology. I tried to explain the two things. First of all, Lux equation tells you by itself how to choose A. And from this choice, it follows that after gauge transformation, something only linear remains in the evolution of eigenvector.
Maybe we will assume at 11:30.